Hi guys, today I'll be showing you about thermodynamics. We'll go through a couple of formulas and I'll show you some examples. So let's begin. What is energy? Energy is the ability to do work, which is the ability to exert a force causing displacement of an object. It is never destroyed nor created, it is only transformed. So the amount of energy in the universe was always the amount of energy in the universe and will always be the amount of energy in the universe. So we have a couple types of energy. There are obviously more than these. We have thermal, so heat, gravitational potential energy, which is when you have a height, nuclear energy, kinetic energy, and basically everything needs energy to move. If you want a car, it needs energy. If you want to move yourself, you need calories, which are a type of energy. So thermodynamics. This is the study of energy and energy transformations. So the law of conservation of energy. So the delta energy in the universe is zero. So the change in energy, delta symbolizes change, is zero, right? We have delta refers to change. So the amount of energy in the universe. So if we split it up, if we say the amount of energy from a system, a specific system that we create, and its surroundings equals zero. So all the surroundings in the universe, the change in that, and the change in the system equals zero. So energy from a specific system emits or receives energy from its surroundings, and the sum is the total energy in the universe. So whatever heat this system gains, this loses. If this system loses, this system gains. There will always be the same amount. So then if we use this formula and we move it around, we say that this delta E of the system is what is lost. You see the negative, and if we change it around, the surroundings gain and the system loses. This way there will always be the same amount in the universe. It just one gives to the other, gives from the other, or takes from the other. So joules. This is the standard unit for energy, SI. A joule is the energy transferred to an object when it moves 1 meter against a force of 1 Newton. So a joule is a Newton times a meter. A Newton is a kilogram meter per square second. So a joule, if you plug this formula in, this is a joule in terms of newtons. Energy. The mass energy equivalence. So this is what Einstein created. This was his theory. So there's a way to calculate the raw energy in a mass. So we have M. The E is in joules for energy. We have M, mass in kilograms, and C is the speed of light in a vacuum, and then it's C squared. So if we give an example, how much pure energy is in 1 kilogram of a substance? So we have M is 1 kilogram. The speed of light is 3.00 times 10 in the power of 8 meters per second. That's the speed of light in the vacuum. And then you calculate. You plug it in, 1 kilogram times 3.00 times 10 to the power of 8 meters per second squared. And this is your final. This is a lot of energy in 1 kilogram. That is like the total raw energy in 1 kilogram of any substance. So kilojoules and moles. So we can also say that 1 kilojoule, right? Kilo for kilogram, right? Kilo for 1,000 is 1,000 joules. So energy is usually measured in kilojoules because joules are a relatively small amount of energy. In this video, we will measure it in joules because of the more simplicity, but I will also show it in kilojoules. And remember that 1 mole is 6.02 times 10 to the power of 23 particles. That's Avogadro's number. And we can also measure energy in terms of moles. So 1 kilojoule per mole is how much energy, how many kilojoules are in a mole of a substance, which is 6.02 times 10 to the power of 23 particles. Heat. So we can measure, we symbolize heat with a Q, which is the transfer of kinetic energy. So we have, so the temperature for T is like, it can be in Celsius or in K for kelvins. Kelvins is the scientific way to do it as well. You could say, so 0 kelvins is minus 273 degrees Celsius. That's absolute zero. That is when there is absolutely no kinetic energy or heat at all. Heat capacity. So we have heat capacity is symbolized by C, and it is the amount of how many joules can be held in 1 gram per degree. So how much energy can be held in 1 gram of a substance per degree. So we have a list of materials here and their specific heat capacities. So aluminium can hold 0.93 joules per gram per Celsius. Iron can hold 0.450, lead 0.130, and water 4.186. This is how many joules can be held in 1 gram per degree. Heat transfer. So remember the Q for heat, formula for the amount of heat something contains or how much was transferred to it. So it's Q equals MC delta T. Remember the delta is the change. So Q is the amount of heat measured in joules, mass of object in grams. It can also be in kilograms, but when you change it to kilograms, also then this formula has to change. In this video, we'll be just using grams and joules. See the specific heat capacity, what I just showed earlier, and delta T, the change in temperature in Celsius. It can also be done in Kelvin, but this video I will be doing it in Celsius. So we'll do an example. How much energy would it take to raise the temperature of water of 100 milliliters by 25 degrees Celsius? So remember that 1 milliliter of pure water is 1 gram. 1 liter of water is 1,000 grams, 1 kilogram. So this is the equivalence. Q, which is the heat transfer, so that's how much heat it would take to raise, how much heat would you have to donate to this water for it to change its temperature. So we have 100 grams, the specific heat capacity, and 25 degrees Celsius, right? Because it's being raised by 25 degrees Celsius, and we get 10,465 joules, or we could also say 10.5 kilojoules. Heat transfer as well. So this is like we had before, the energy of a system and energy of its surroundings. So here we also have the heat of a system. The heat gained by a specific system is the heat lost by its surroundings, right? The amount of heat in the universe, like energy, is the same. Heat and energy are the same thing. And so when one loses, one gains. And remember that heat is always, in all cases, transferred from the object at the higher temperature to the object with the lower temperature. So I'll give an example. If 20 milliliters of cold water at 4 degrees Celsius is mixed with 50 milliliters of warm water at 50 degrees Celsius, what will be the final temperature? So we have a couple of formulas that we're going to use. We're going to have the heat, right? The heat formula, how much one gain, one loses. The Q equals MCT, so how much is donated, right? The mass, specific heat capacity, and delta T. And delta T is the final TF, the final temperature, minus the TI, the original temperature. So what we are looking for, we're looking for the final temperature. What will be the final temperature? So we make a chart here. Variable, mass, specific heat capacity, and original temperature, the TI, initial temperature. So we have 20 grams, right? 20 milliliters is 20 grams. 50 milliliters is 50 grams. Both have the same specific heat capacity because they're both water. And this one originally is at 4 degrees Celsius, and this one originally is at 50 degrees Celsius. Now let's do the question. So we say Q system, so the heat gained by this system is what's lost in the surrounding system, right? The cold water is going into the warm water, right? So the warm water, like we had before, heat is always transferred from the object at the higher temperature. So the higher temperature is losing out, so that's why it has minus, the negative symbol. And so we do the formula. We plug it in 20 grams, TF minus 4 degrees Celsius, and we have negative 50 grams, TF minus 50 degrees Celsius. And notice that the C is being canceled out, right? The C, we don't mention the C in this part because the C, both C's are the same thing. So we can just cross it out from the beginning. And then we can algebraically open this up. 20 TF minus 80 gives us this. We put it together. And then the TF, the final temperature, is 36.9 degrees Celsius when you would mix those two waters. So heat capacity. So whatever has a higher heat capacity will gain heat slower and lose heat slower. So whatever has a higher heat capacity. So here we have water will gain heat slower and will lose heat slower than any of the rest because it has a higher heat capacity. And whatever has a lower heat capacity will gain heat faster and lose heat faster. So the lowest one here, lead, 0.130, will gain heat faster and lose heat faster than the rest because it has the lowest one here on the chart. So, another example. How much energy does it take to raise the temperature of 100 grams of aluminium from 30 degrees to 45 degrees Celsius? So we have the Q for heat transfer, MC delta T. M is 100 grams, right? We have 100 grams. The C we got from before from the chart, 0.930 joules grams per centimeter per Celsius. And the change in temperature is the final temperature is 45 degrees. The original temperature is 30, and that gives us 15 when you subtract them. And then when you plug them in to this equation, you get 1,354.5 joules. And if you divide by 1,000, that's how many kilojoules you will have. Another example. 1.6 kilograms of ibisium, that's an imaginary substance that I made up, at 14 degrees Celsius, is placed in 2 liters of water at 34 degrees Celsius. If the final temperature at equilibrium is at 21 degrees Celsius, what is the specific heat capacity of ibisium? So remember that energy is gained in the ibisium because it has the lower heat than the water, right? Water is 34, ibisium is 14. And we're going to use the formulas, the Q formula, the MCT formula, and we're looking for C, the specific heat capacity of ibisium. So we have all these things here, right? 1.7 kilograms is 1,700 grams. 2 liters of water is 2,000 grams. The change in temperature here, water loses 13 degrees Celsius, and ibisium gains 7 degrees Celsius, and we have the specific heat capacity here as well. So now let's do the calculation, right? We have the Q, we have the loss here, the gain in the system, the loss in the surroundings, right? Because it's going in and it's taking from the surroundings. So X is what we don't know. This is specific heat capacity, right? Joules per gram degree Celsius. We plug this in algebraically. We solve for this, right? This is what we get at the end, and when we apply each one here algebraically, this is what we get. And when you divide 100,836 divided by 11,900, you get about 9.1459 joules per gram Celsius. So that is your specific heat capacity for ibisium. It's not a real material. I just made it up for the sake of the question. And now for the final question. A 1-ton car is traveling at 30 meters per second and brakes until it stops. The brakes are made out of 30 kilograms of iron and absorb all the energy. What is the increase in temperature of the brakes? So this is a new one, kinetic energy. It is the energy in an object that is in motion, symbolized by E subscript with a K. So any object that is in motion has kinetic energy. And the formula for kinetic energy is half multiplied by the mass in kilograms multiplied by V, the speed. Right? The speed is meters per second. So the EK of this car, 1 ton is 1,000 kilograms and 30 meters per second. And it should be squared. When that's squared, you get 450,000 joules. That's how much. That's a lot of energy that's passing through the car. And now what you have to do is energy is lost from the motion, right? So it's lost. The energy when it stops, it now has 0 kinetic energy. So that means from the 450,000 to 0, it lost energy, and the energy went to the brakes to stop the car. So that's gained in heat, right? So we have MCT equals 450,000 joules. We have the 30 kilograms, right? 30,000 grams is 30 kilograms. This is from the brakes. The iron heat capacity, remember the iron was what was made out of the brakes. The change in temperature and how much was lost from the kinetic energy. Now then we do the calculation here, and we solve for T algebraically, and we get about 33.33333 degrees Celsius. So the brakes had a change of temperature of about 33 degrees Celsius. That's why when a car brakes, it's moving really fast. The energy moves to the brakes at the end when it stops totally, and the brakes get really, really hot. That's why you can't touch them. I hope you found this video helpful and the content useful. Please consider subscribing and sharing it with your friends and everyone that you know. Thank you very much.